Today, we're going to be adventurous angle chasers, chasing down those nifty angles you can't find. But first, let's start off with the basics. The sum of angles in a triangle is 180, of course, and the isosceles triangle property of a triangle is that in an isosceles triangle, if the two sides are equal, then the two corresponding angles are equal. And similarly, if the two corresponding angles were equal, then the two sides are also equal as well. So basically, it's multi-directional. The sides equal means the angles equal means the sides equal. Okay, so opposite angles in intersecting lines are equal. This is known as vertical angles, right? These two angles equal. Corresponding angles in pair. Let's explore them here. So we've got, of course, complementary angles if they sum to 90 degrees. Supplementary angles, if they're on a line, they sum to 180. Again, vertical angles, these two angles are equal, these two equal. Parallel line angles, and like there's these corresponding angles that are always equal. And then we can also derive other relations like alternate interior angles, like we know this is equal to this, or alternate exterior angles, something like that, and many other relations by using the supplementary properties for each of these points over here. So we have a bunch of angular relations with parallel lines as well. And now let's just try a simple example that uses all of these properties. What is the angle measure of this angle A? So the interesting thing about this problem is it's not just a simple triangle or parallel lines. We got a more interesting configuration here. Let's see what we should do. So first of all, we know this is 100 and this is 110. That means that this angle over here must be 70 because of supplementary. And this angle must be 80 because of supplementary as well. Oh, but then we see 40, 70, and blank. The sum of angles in a triangle is 180. So 40 plus 70 plus that angle here, let's call it x, is 180. And that means 110 plus x is 180, or x is 70. So this thing over here is 70. And now, vertical angle. So this is also going to be 70. Now the thing is, we were trying to find A, right? So that's why we don't really care about this half of the diagram. We're mainly trying to focus on the angles over here so that maybe we can try to find this angle. Now with the information present, do you see a way to find angle A? Pause the video and think about this for yourself for maybe a minute or so. We've got a 70-degree angle here, an 80-degree angle here, and therefore the sum of angles in this triangle is 180. So we have 80 plus 70 plus angle A is 180, or angle A is 180 minus 80 plus 70, which is 150, 30. So 30 degrees is going to be our answer. Key idea was just using the information, finding other angles based on that, and then trying to aim to find the angles closer to A and realize that you don't have to find every single angle in the diagram. Okay, let's try a slightly more interesting example. Okay, so over here, in acute triangle ABC, D and E are points inside triangle ABC such that DE is parallel to BC. B is closer to D than it is to E. So it's just saying that D is on the left side, E is on the right side in this diagram. Luckily, we've got a nice diagram showing everything for us. Okay, so now here are the angle conditions. Let's take a close look at them. AED is 80, so that's 80. ABD is 10, so that's 10. CBD is 40. 40. Find the measure of angle BAE. Okay, BAE. We only have 3 angles here. That's not a lot. But the main condition that we're given that seems to be kind of like the ruling one in this problem is DE parallel to BC. And the key thing to note here is that this is a transversal through the E and BC, if you can imagine that. And parallel lines, we know those have a bunch of special angle properties, right? Let's see what some of them are. And so parallel lines. Oh, we've got this angle. Corresponding angles. This will be equal to this angle, right? Because they're parallel lines. And by the way, if you're wondering why this is true, it's because you can kind of just move. It's a translation. You can move this down here, and it's the same angle because they're parallel. So by corresponding angles, because of the parallel lines, we know this angle is equal to that angle over here. So that's also 80. BAE. Now, let's call that angle x. We have that x plus, now notice how this angle here is part of this triangle. It's part of a triangle, right? So we have x plus 80 plus this angle, and that angle is just 40 plus 10. And 40 plus 10 is just equal to 50. That's equal to 180. So x equals 180 minus 130 equal to 50 degrees. Wow. So it seems like such a complicated diagram, doesn't it? But the key thing was just to focus in on the key parts, these parallel lines, which gave us these two angles equal, and then these two angles we knew, and then we realized that this, despite this diagram having a lot of extra clutter, we're just trying to find this angle, which is part of a big triangle like that. So just 50. Now we're going to learn this property called inscribed angles and the inscribed arc theorem. You might already be familiar with this, but all it says is that this angle here, A, will be half of the angle of the arc. And what is the angle of the arc? The angle of the arc, and of course this is in a circle, the angle of the arc is the angle formed by the center of the circle right here. So essentially what that means is that, let's take a circle. And I can draw a perfect circle because, boom, perfect circle, magic. Okay, and now with this circle, imagine this is the center of the circle. That red point over there is the center of the circle. Now what this essentially is saying is that this arc, let's imagine this arc over here. Whatever this measure is, let's say it's 2a, we can take any inscribed angle, so any point on the circle, and connect it to these points over here, and this angle will just be half of that central angle. And that's true for not just one point, but any 2 points. So pick any point on the circle, any point on the circle that's not here, like you can't pick this thing, for example. So any point on the circle from here to here, and essentially this angle here will be half of the central arc in the center. Isn't that cool? That it's true for anything. So it doesn't matter what point you pick on the circle, as long as the point is between these 2 points, that will form an inscribed angle in them. So essentially the angle over here is inscribed in this arc, so its measure over here will be half that of the arc measure, or which is the same thing as half of this angle here. And that's true for anything. So the key part about that is it allows us to say that these two angles, they're equal because they're both inscribed in the same arc. And that's the power of this inscribed arc theorem. And we're going to about to explore a really cool application of the inscribed angle theorem. Okay, we've got a regular octagon. Let's do blue for this problem. Let's draw a nice octagon, and I'm better at math than I am at drawing, so forgive me if this drawing is not that good. So we've got a nice little octagon here. Whoops. And it's a regular octagon as much as, so A, B, C, D, E, F, G, H. And let's label it A, B, C, D, E, F, G, H. Find the measure of angle ACF. Okay, so we got this random ACF. Hmm. This is a very strange angle, isn't it? It's not like a interior angle or anything. It's just a strange angle appearing in the middle of nowhere. What is this? I mean, there's many ways to solve this actually. One way is to do a giant, really messy angle chase using these angles and then some these angles, and believe me, it's not going to be easy at all. Is there an easier way to do this? Hmm. There's a really neat little trick here, and okay, I want you to focus in on this angle. Does it look like anything we just learned? It looks like it's kind of inscribed in the octagon, doesn't it? But hmm, we're not talking. Inscribed angle theorem doesn't deal with inscribed octagons. It deals with inscribed in a circle. How is this theorem going to help us here? Well, if there's no circle, we can just draw one. It's as simple as that, really. So we can just draw a nice. Whoops. Let's draw a nice circle. Hopefully it's not too egg shaped. It's looking pretty egg shaped so far. Okay, so this is a nice circle. Very good, well drawn circle, as you can see. But in this circle, notice how this angle over here is inscribed in the arc AF. And essentially, we already remember that the arc measure is just the measure of the interior angle those 2 points form at the center of the circle. So we already know that this angle right here is going to be half the measure of this arc. Aha! So now we just made this random angle in an octagon the measure of a simple, nice arc. So how do we find the measure of this arc? Or essentially, it's the same thing as the measure of this angle here. Well, the key thing here is that we can divide. Let's use red for this time. So the key thing here is we can imagine drawing lines here, 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 here. These are all going to be congruent triangles that are the exact same. Because we can imagine dividing this octagon into 8 pieces. Octagons are symmetric, right? So if octagons are symmetric, we can divide it up into these 8 identical triangles. They're all the same. And the key part here is that if they're all the same, then we can imagine all of these 8 angles to also be the same. And the reason they're all the same is because in octagon, it's regular. It's going to be symmetric. Fully symmetric 8-dimensional symmetry. So all of these angles here are going to be divided up equally. Another way of thinking about it is that each section on this arc is going to be equal as well, because like I said earlier, the octagon is symmetric, so each of those arcs are going to be the same. So we know each of these angles are going to be the same, and this over here, A to F, the arc AF, or the angle from here to here, takes up 3x. It's 3x degrees, right? 3x degrees is the measure of this arc, AOF, or AF, the arc there. And there's a total of 8x in the full circle. We know there's 360 degrees in a circle. So this whole thing, 8x is 360, right? The total sum. So 3x will be 3/8 times 360, and 3, which is the same thing as, let's move over to the other side. 360 divided by 8 times 3, which is 45 times 3, 135. So we know that this angle, let's draw it in, is going to be 135 degrees, which is the same thing as the measure of this arc. And now, by the inscribed angle theorem, we know that this angle over here will be half of this angle over here. We already discovered this angle to be 135. This angle will be half of that, 135 divided by 2. right? Inscribed angles are half of the arc angles. So it's just 135 over 2 degrees, and we are done. Isn't that crazy? How we simply drew a circle around it and then used the inscribed angle theorem to deal with this strange angle in the octagon? That's a pretty cool trick if you ask me. And just to summarize, the key ideas were drawing a circle around it, then seeing the inscribed arc was just the arc that it was inscribed in was 3/8 of 360 or 135 degrees, right? That was this arc over here. This arc, the angle of this central angle or this arc was 135. So the inscribed angle was half of that, ACF. And that was it for this problem. Okay, now we're ready to move on to this inscribed right triangle here. And the key cool thing is, you know how inscribed angle theorem states that it's inscribed is half the central angle or arc. If the central angle over here is 180 degrees, so you can imagine this over here is 180 degrees. Now this over here will be half of 180, so 90, because that angle is inscribed in the 180 degree arc, so half of 180. Same thing about this angle right here, half of 180 by the inscribed angle theorem. So that's why any triangle that has hypotenuse, any triangle that has this as one of its sides will be a right triangle. So you can pick any point on the circle on both sides this time, and it's going to form a right triangle. Always it will form, whether it's this or any other point. Infinite possibilities. Now we're moving on to polygons. The sum of the interior angles in a polygon is n minus 2 times 180. And just to show you, I'll show you a quick example of the pentagon about why this is actually true. Okay, so imagine over here, we can divide this into 3 triangles. And each of the 3 purple parts, the purple parts sum to 180, as you can see there, because of triangle sum, angle sum. Each of these blue parts sums to 180 as well, because it's a triangle. And each of these, let's say, red parts sum to 180 as well. So the overall sum of the purple, blue, and red parts is 540. 3 times 180. Because these make up all the angles in the total angle sum in a pentagon. So 3 times 180. And similar logic works for any polygon. We could break it up into n minus 2 triangles, each with a sum of 180. And if it's a regular polygon, then we have that the any interior angle will be n minus 2 divided by n times 180, right? Just this formula over here divided by n, which is the number of angles in the polygon. And another cool property is that the exterior angle of any regular polygon with n sides is 360 over n. So if we have a 20-sided polygon, 20 is a big number, right? Exterior angle, super easy to find. Just 360 divided by 20. Simple as that. And here's a table it's good to memorize. It's not necessary. I mean, you can always calculate it, of course, but it's good to memorize that, of course, 3 is 60, 490, 5 108, 6 120, 8 135, 9 140, 10 144. It can be a good thing to memorize that. Okay, but now we're going to move on to this interesting math counts problem. A square is located in the interior of a regular hexagon, and certain vertices are labeled as shown. What is the measure of ABC? So it's not even drawn in for us, so let's do that real quick. ABC, just like that. Okay, so we've got a square, we've got a hexagon. They're both regular, right? Square is a regular quadrilateral. So let's see, what are the angles we know? We know a square, which is a regular quadrilateral, has 4 angles of 90 degrees. And hexagon, well, you can just look at this table to see 6 is 120, or you can just apply the formula n minus 2 over n times 180, which for 6 is 6 minus 2, 4 over 6 times 180, which is 2/3 180 or 120. So in a regular hexagon, each angle is 120 degrees. Oh, so let's draw that in real quick. Oh, let me use a different one. That is 120 degrees, the blue angle. So this over here is 90 degrees. The big blue angle is 120 degrees. So that means we must have, let's use purple here. This part over here must be 30 degrees because the whole angle is 120 and then just this part is 90. So the part over here is 120 minus 90, 30. And now here's really where the key observation of the problem is. Regular hexagon, regular quadrilateral. They share a side, right? And because they're regular, all of the sides of their polygon will be equal. Regular polygons always have all the same angles and all the same sides. So all the sides of the square are going to be that same x because it's regular. Similarly, all the sides of the hexagons are going to be that same x as well because it's a regular hexagon. Okay, let's go back to what we're looking for. A, B, C. So sometimes to solve these kinds of problems, it requires a little bit of backwards thinking. ABC, it's like this full angle piece minus this part over here. So if we could just find this part, we could find this angle too, because their sum would be the interior angle of a regular hexagon, 120 degrees. But how do we find this here? Somehow can we use this information we have? Also, the key thing to notice here is x, right? Because of they're both sides of a regular polygon. And notice how the side length of the square and hexagon are equal. And that means that these two side lengths are equal as well. And we're looking for this angle. Does anything click right now? Any property we learned? Indeed. Notice here that because let's mark these two sides equal by the isosceles triangle notation, these angles, they're going to be equal as well. It's an isosceles triangle. This over here is an isosceles triangle. So these two sides are equal, so these base angles are as well. So x 30, we must have 2x plus 30 equals 180. So 2x is 150, or x is 75. So these are both going to be 75, 75. Cool. So like we already discovered, if we could just find this angle, we would easily find this angle as well. Now let's just call this angle y, angle ABC. We have that y plus 75 equals this whole angle, which is just the interior angle of a regular hexagon, 120, which we already just found. And now we simply have that y is 120 minus 75, which is 45. So our answer is just 45. The key idea for this problem was looking at the angles of the square and hexagon that we knew, right? We found this was 90, then this was 30. And then the observation was that the side lengths of the square and hexagon are equal because they share a side. And that means we've got an isosceles triangle here, which we can easily use to find this angle, which allows us to find this angle because of the total sum, the interior angle of a regular hexagon. And you can check out, and there are some advanced angle chasing theorems, which I'm not going to cover in this video, but if you're interested in them, you can check out my AMC 10-12 angle chasing video. I covered these and even used some of them. But for now, we're going to move on to the next chapter. We're going to move on. And by the way, you can find all of these problems, practice problems, in the Mastering AMC 8 book, which contains plenty of videos and problems and examples for practice. You can click on the link. It's completely free to download and use. We're now ready to move on to triangles. And angle chasing is very useful in triangles, but triangles have some cool properties like Heron's formula, in radius, and we're going to explore a bunch of these properties in the next video. Click on it right there.